All right, let's do a few questions. We'll do this first one up on the left about the capacitors first. Remember your relationship for capacitors, how we describe the capacitance based on the geometric dimensions of that capacitor. Do y'all remember what it is? C is equal to what? What is it?
A, E,
Yeah.
F,
Kappa, epsilon, A over D. Kaylee, I think you said that C is equal to Q over V or something like that. It is true, too, that Q is equal to CV, but that's not the relevant expression in this case. That's not the relevant equation in this case. All right, let's stop at 103. 103. Okay. D is right. That if I double A, I double D. Remember we talked about capacitors? They're kind of like a big bowl that you put popcorn in. If you make the bowl bigger, I can just hold more popcorn in it, right? So similarly, if I make the capacitors bigger, if I make those plates bigger, they can hold more charge. Let me ask you a question. What if the area of the plates and the distance, D, between the plates, what if both of those are doubled? Then what happens to the capacitance? I make the plates bigger and I move them farther apart. What's going to happen to my capacitance? Oh wait, never mind. I'm sorry, it's not on there.
Yeah.
Okay, the answer is E. You got that E, everybody? No, you don't all have it. Put E for crying out loud. There you go. All right. All right, so if I double both of them, then I'm going to have a factor of 1 over here. It's not going to change. So moving my plates farther apart actually reduces the capacitance. Making them bigger actually increases the capacity to store charge. Moving them farther apart, you can think of it like I'm spreading that energy out over a bigger area. And because I'm doing that, there's just not enough energy there to bring the electrons onto the plate. Well, let's do this one about resistors. What do they do to the flow of electricity in a circuit? All right, let's stop at 30. Very good. D is right. They limit or resist the flow of electricity. All right, D is right. Say a guy walks into a bar and he has what do you call them, like jumper cables around his neck, and the bartender says, "Hey, you can come in here, but you better not try to start anything." Yeah, no, very good sense of humor. That's a very funny joke. Yeah, I know. All right. What are the units for electric potential? Remember, electric potential, that's V, or voltage. Huh? All right, let's stop at 40? All right, he is right. It's volts. So remember, there are some alternative answers that you could have for electric potential. It could also be volts, or it could be joules per coulomb. Joules per coulomb. And the reason is that electric potential is energy per charge. And energy is measured in joules, and charge is measured in coulombs. All right, let's do this one down here. What's going to happen to this particle? I think this was on the quiz. Was this on the quiz recently?
Yeah.
Both of them? Awesome. All right, let's stop at 30. Good job. Awesome. That's right. It's going to, a positive charge will always move from high to low potential. Remember, negative charges move from low to high potential, but a positive charge will always move from high to low. And so if I were to put the charges on this, because these are charged plates, this would be the positive side, and this would be the negative side. And so it's going to experience a force in that direction, and then also the electric field lines will point in that same direction. Okay? What's the difference between a, goodness bless you, what's the difference between a cat and a complex sentence? You've never thought about this, have you? A cat has claws at the end of its paws, and a complex sentence has a pause at the end of its claws. All right, let's try this last one. All right, let's put up about 10 or so seconds. Oh yeah, so R for resistance is rho L over A. It's on your equation sheet. Think first, if I have a wire and I just make it bigger, is it easier or harder to push electricity through that bigger wire? It's easier, right? It's like a big pipe. If I have a big pipe, I make it bigger, it's easier to push liquid through that pipe. It's a similar thing, that there's just more space for the charges to move through. So a bigger wire has less resistance. So I know that the answer cannot be this, this, or this. Right? Because my area got bigger, right?
I thought it was D.
No, the area got bigger. I just told you. So the resistance.
I'm saying, what is the resistance?
Oh, yes. I'm sorry. The resistance has to go down. So it's either C, D, or E. All right? Let's stop at 150. All right. So what did I do? I doubled my area. If I double my area, that halves my resistance. So the resistance was 12, now it's going to be 6. We had a similar question to this, but it wasn't the area that was changing. I mean, the area was changing, but I didn't tell you the area. I told you how the radius or the diameter has changed. And in that case, it's an inverse square relationship. But here, I double this, so I have the resistance. Okay? You with me on that?
No.
No? So let me step through. Right, so the cross-sectional area went from 2 square meters to 4 square meters. It doubled. I multiplied this times 2 to get this. So that's where this 2 comes from. It's what did I multiply it times? Like the same answer would be if I changed this to say 3, and then what would this be? 6. That would have the same answer because 3 times 2 is 6. And so since I've doubled the length, double the, let's see, where is it? I'm sorry, it should be 3 and 6 right there.
If you plug it into the formula, though,
Don't do it.
it wouldn't work.
No, you can do that. Can you do that?
It works. 4 divided by 2 is 2, and then divide by 2.
Oh yeah, that's fine. All right. So I want to look at how the area is changing. My area is doubling here. I go from 3 to 6 square meters. So in my equation, I say, oh, my area is doubled. And how is that going to affect my resistance? But you can think of it, too, just from a qualitative perspective, that if I make my pipe bigger, it's going to be easier to push that electricity through. So my resistance is going to go down. And then I get rid of several options. And I just have some options that are left, only 2 options that are left. Okay? Yes, with me? Okay. Yeah. All right, let's look at electricity in the body. Oh, wait, no, what's this? Oh, yeah, so also energy. Energy will come back a little bit. But if I have electricity going through a resistor, it will expend energy. In the lab for this class, or not for this class, for the second semester of physics, we build a lot of circuits, and so they hook up resistors to power supplies, and they measure the voltage and the current and all that. But almost every lab, somebody burns up a resistor because they put too much current through a resistor, and those resistors they get really hot right at first, and then they smell really bad, and then they start smoking, and then usually there are like squeals of excitement coming from the lab groups. And we have to never had an actual fire. Nobody's ever been hurt. But when you put electricity through a device, it expends a lot of energy, right? That electrical energy comes out. We can describe that U. Remember, this is energy, potential energy. Before we had said that V is equal to U divided by Q. That's how we defined potential, energy per charge. And so this energy is just going to be Q times V. And since power is energy per time, we've seen power before. We saw that in Chapter 3 on the work and energy chapter. Power, remember, is measured in watts. It's joules per second. It tells how much energy you're using or you're radiating in a given amount of time. Since power is energy per time, if I just divide both of these things by time, what is this expression right here? What is Q divided by T? Charge per time. And we've seen that. What is a charge per time? What do we call that? We just saw it a few minutes ago, 5 minutes ago. What is a charge per time? How many coulombs of charge pass a point in a given amount of time? Yeah, you're right, Jay. That's awesome. Yeah, it's called current. So that's our current, which is I. And so I can replace this business with an I, and I get the expression for power, which is P equals I times V. So for example, if I have a light bulb that has 120 volts and a current of 2 amps, then my power is equal to 2 amps times 120 volts. That's a pretty big light bulb. It's a 240 watt light bulb. Remember, these are the units. Watt are the units for power. A joule per second. Electricians use this a lot when they're mapping out homes, they need to know how much current is a home going to use in a particular circuit, right? Because your circuits in your house, they're all rated to a certain current, 15 amps or 20 amps or maybe 30 amps on some of your bigger circuits. And so they'll go through and they'll say, oh, a toaster. If you're going to have a toaster hooked up on this circuit, then it has a power rating of, say, 1,200 watts. Toasters use a lot of energy. Anytime you're producing heat with electricity, it requires a lot of energy. And the voltage in your house is 120 volts. And so they say, what is the current that thing's going to pull? Because you don't want too much current. If you pull too much current in your house, what's going to happen? It won't short. It'll do what? Yeah, the breaker will kick off. Y'all have all had that, right? When you turn on the microwave and the hairdryer and the this and the that, you have too much stuff going, and it just kicks off the circuit breaker. And so they have to know how much current is going to be on each one. Well, I is equal to P divided by V. That comes from this. P is 1,200 watts. Divided by V is 120 volts. And that's equal to, how many times is 120 going to 1,200? How many? 10, right. So it's 10 amps. You could see a question like that on the test where I ask you, I have this device, how much current does it draw? Okay? And so, for example, if you're already pulling 10 amps, then your electrician better limit the number of outlets for that particular circuit because you're not getting that much more. If you hook up another toaster, then you've exceeded the maximum current that you can have. And you don't want that. You don't want to be going out to your circuit breaker all day. It's not good for your house. All right. Electricity in the body. We've seen static electricity. I brought the Van de Graaff generator, right? Yeah. Yeah. So static electricity refers to the buildup of excess charge. It was that day that it worked really well, right? Like, didn't you do it? Yeah? And like your hair was, yeah. I mean, you could feel it on your eye, What are these called? Lashes? Oh, okay. It refers to the buildup of excess charge on an object. So, for example, when you have that Van de Graaff generator, you can just get a lot of charge, a lot of electrons that are on your body. Most of the charge on the human body is on the skin or hair. So that's why on dry days, why on dry days? I said this. What is it about humid days that doesn't really allow for the transfer of charge very easily? The water, because water is a what type of molecule? It's a polar molecule, so it's a little bit negative on one side and a little bit positive on the other, and as it bumps up against you, it takes away those excess charges. So most charge, let's just sort of make that. So what did I say? Water is a polar molecule. Something like that. I'm not a chemist. Which side's positive? Do y'all know? I think the O side is negative. Is that right? So this is sort of a negative side. That's the positive side, and so it will take away excess charge. So humidity, the water in the air, takes away excess charge. I can read that? That's my handwriting in this class. Is it okay? Can y'all read my handwriting? Yeah? Y'all know I made 2 Ds in my academic life. I made a D in engineering math when I was a sophomore in college. And you know, meh, it's engineering math. Not that embarrassed by that, really. It was a tough class. And I goofed off. That was really it. I just goofed off too much. And then I also made a D in the 4th grade in handwriting. because I'm left-handed, and left-handed people, right? Just, maybe we don't write as well as you right-handed people. But we can do other things better than right-handed people. Who's left-handed? Somebody's like, yes, right? So I made a D in handwriting, and my teacher, Mrs. Harris, she outfitted me with this pencil that you would sort of hold, and it was supposed to teach you how to hold your pencil correctly, and it had this strap that went around your hand. It's like, so I guess you wouldn't fling out of your hand when you got frustrated, but they were trying to teach me to write correctly. Did they do that to you? No?
We used like special paper. Like it had
The trace the letter.
no, it was like graphic paper
Oh, yeah?
because I would write very close together, and they couldn't understand it. And
I have to do this thing like a page like that.
Uh-huh, yeah, yeah. Yeah, that's crazy. Anyway, that's a tangent. All right, so the body can conduct electricity. But the current you experience is dependent on the voltage and the resistance. Right? I is equal to V over R. So that's Ohm's law. The current is dependent upon V and on R. And because wet skin has a lower resistance, so V is equal to I times R. If this stays constant, if this goes down, that means this goes up. It's an inverse relationship. So if you have a lower resistance, that means you have a larger current. There's a table of currents and their effects on people, sort of how it feels. It's in your book. Most people can feel, you don't need to know the numbers, but just for your reference, most people can feel 1 milliamp, 100 milliamps can cause fatal defibrillation. Like the heart stops working with just 100 milliamps. And if you have 300 milliamps, that causes burns. And if you have an actual defibrillator, clear, paddle, that's 6,000 amps. I don't know how they work exactly, but your book just gives those in the table. You can do defibrillation that uses a much smaller current, that when they open up your heart, they can actually defibrillate your heart. You want to know about this?
With the little.
Right, a little bitty. Yeah. Can you remember that?
No,
On television? Yeah. Wow.
Where does it put people's mouths at work?
Okay, I say you don't need to know those numbers, it's just sort of for your reference. The amount of current their body receives is heavily dependent on the path that it takes. Because different parts of your body have a different resistance. So, for example, hand to foot. Will be a much larger resistance. Just because, I'm going from here all the way down to my feet. It's a big, long space to go through. And it's like if L goes up, that means the resistance also goes up. R is equal to rho L over A. So if I have a larger resistance, I have a smaller current. I, V, R. If R goes up, I'm sorry, that's all wrong, isn't it? Do you need to erase? You didn't write it down. You're awesome. V is equal to I times R. If R goes up, I goes down. The Then from, say, your index finger to your thumb. So from index finger to thumb, L is really small, so the resistance is really small. Okay? You can feel electricity just sort of from this or across your index finger to your thumb, across that area too. In fact, electricians used to, they have nice tools now, but some of your old school electricians, they just use their fingers to test. Hey, is that wire hot? And they go, zzz, and test it. So a lot of your older electricians, they can't really feel their hands very well because they've shocked them so many times throughout the years. Or if it goes across your chest, that can be a lower resistance than, say, if it went from your hand all the way down to the foot. And a nice application of this is the E-meter. Any Scientologists in the class? No? Probably never. I don't. Scientology, it's a religious group. It's a cult. But, yeah, it's a cult. But if you're Scientologist, I'm sorry, I don't want to offend you, but it's a cult. But anyway, they use the E-meter. Oh. So don't go to the next page. But they use this E-meter. Here's a picture, and I'll show you a video here in just a second. And basically, this is from Scientology. It measures, the E-meter measures the resistance of the body. And they use it to look for things like deceit. Like they're lying to them. They use it sort of like as a lie detector. You hold these paddles in your hand, these metal cans, and if you're telling a lie, it'll show up on the E-meter. The resistance of your body will change. For a variety of reasons. Your hands get sweaty. That changes your resistance. Your heart might pump faster, so you just have more fluid going on in your chest. Your body chemistry might change. So there's minute changes in your body that will change the resistance of your body. And because it's such a sensitive instrument, measuring that resistance, it'll show up on the dial. And so they take you. I took a class on cults once. It's kind of, I mean, it's terrible, right? Because they're trying to make you do things that you might not otherwise do. But they use these things to guide you through these questions and to sort of explore things that you've done in the past, and then to try to manipulate into you to doing other things. Yeah, see?
There's a TV show about that.
Is that right? Oh.
Yeah, like, it's about like people who have like been through it and stuff.
Yeah.
Like survivors.
Wow. Yeah. Those people do crazy things. I have a video I want to show you. It's just about, it's not about, it's about the E-meter in particular. All right, so they use the E-meter to find psychological issues. So they sort of use it from a counseling perspective, but it's not counseling, like it's manipulation. It's trying to manipulate you to various things. Never had a Scientologist. Maybe we have one. I'm sorry if I'm upsetting you, but apply our E-meter and see if anybody is a real Scientologist. I don't think there are many in Thibodeau, but there in other cities there are a lot, because it's a fairly influential cult. All right, let's look at the in-body. The in-body, y'all have probably seen a device like this before, right? Y'all seen something like this? I know they have one here at the rec center, and they have one that's sort of like that at the wellness center at the hospital. But this is a device, the one they have here at Nichols. You stand on it kind of like a scale, but you hold these two handles, and it sends an electric current through your body. You can't feel it, but it sends an electric current through your body. You have to take your shoes off and wet your bottom of your feet and stuff so that there's good contact for the electrical current to go through your body. And then as it goes through that, it measures things like the water content of your body, the mass of your body. So I think I've shown this to y'all before. This was me. This is not actually a picture of me. I told y'all, right? Not a picture of me. Did I show y'all this before? Yeah, so these are my in bodies. They were from, what was it? They were a year or two apart. Yeah, one's in September 2014, and then the next was May 2015. And in between those two times, I had can I see yours? Yeah, it's not working. Oh, yeah. So in between those times, I started lifting weights. And so this, it looks like 182. It's actually a 152 right here. And so going from 152 to 163, I gained all this weight. But if you look, it was mostly muscle mass. I went from 77 up to 83 pounds, so 84 pounds or so. So a lot of that was muscle mass. And it helps you to figure out, okay, how much of this weight have you gained is actual muscle, and how much of it is fat, or how much is water. But it helps you to look at those things. It also has the BMI. Didn't we talk about BMI back in the work and energy? Yeah. We did BMR. Did we do BMI?
Oh, no.
No, well, BMI is your body mass index, I think.
I think it's actually on it.
Yeah. Anyway, it talks about that there. But this particular in-body, the one at the Wellness Center doesn't do this, but the Rec Center does, is it's segmented, so it looks at different parts of your body. So you see here, this was before I started lifting weights, and my legs were sort of over, but my upper body was normal. But then over here, but then my arms were over, and my lower part was normal. So it was still a little disproportional, but it is switched in the opposite direction. All right, so this allows you to measure muscle and body fat mass. Do they have one on campus back in your department? Or something similar? For athletic training folk? Yeah, no? In athletics? Athletics, you'll have one? And it's also segmented. So it gives results for different body parts. Parts of the body. I have a video to show you. It's like an ad for the in-body, but it's fairly interesting. All right, can I take this away? Come back to it. Okay. All right. So let's look at the nervous system. The nervous system uses nerve cells to transmit information through the flow of an electric charge. And we'll look at how these nerve cells function and the different parts of the nervous system, the physics behind it. They don't work exactly like a circuit. They work a little bit differently from how we think of charge flowing through a wire. But you can think of it very much as charge flowing through a wire. Different purposes. You have sensory input, 3 different purposes of the nervous system. So that's input from the surroundings. External stimuli. And the other organ systems. And then that's going to be internal stimuli. And we'll later call this the PNS, the peripheral nervous system. We'll talk about that in a bit. The integration processes, this processes the sensory input. So it takes all that stuff that it gets from outside of your body and inside of your body, and it just processes the sensory input. And later we'll talk about this. We'll call this the CNS. Do y'all know what the CNS stands for? Central. So it's the peripheral and then the central. And then there's also motor output, which is part of the peripheral. So the nervous system causes the body to respond. We'll talk more about that in just a bit, like how the body responds to these different stimuli and the organ system sending information like, oh, things aren't going right, that your body can respond to those things. We have two main parts to the nervous system. There's the central, the CNS. That includes the spinal cord and the brain and the spinal cord. And then the peripheral nervous system. And the PNS, the peripheral nervous system, accomplishes the sensory input. Goodness bless you. And then the central nervous system takes care of what? The what? Starts with an I. The integration. Thank you. Okay. And it sends the information for motor output through the PNS. Okay, that all seems really simple, and it is sort of simple, but I mean, as you know, the nervous system is quite complicated. It accomplishes tasks that are remarkable. We have two types of nerve tissue. Neuron and support cells. Y'all looked at the nervous system in this way? Some of you have in anatomy. So you have the neuron and support cells. The neurons actually transmit the electrical signal. While the support cells are the neuroglia. Am I saying that right? Neuroglia. In that video, we don't say that word impedance. We don't say it that way. That has a different meaning when we say it right. We say impedance is usually the other word that they use for resistance. But anyway, the neuroglia. Are you making that up? Okay. She probably knows, he or she probably knows what they're talking about. So they provide various roles of support for the neurons, such as, for example, the myelin sheath. Which helps the electrical signals to flow in the neurons. And we'll be mainly concerned with the neurons. Like we'll sort of talk about those a little bit, those support cells, but mainly we're looking at the neurons. Goodness bless you. Okay, this is sort of your typical figure of a neuron, and like with the other systems, I'll give you that figure and I'll ask you to identify different parts of it, like we did with the ear and the eye and the like. So make sure that you know the different parts of the neuron. It consists of a cell body with dendrites and axons. Let's see, so this is going to be a dendrite right here. There's little fibrous things that come off. The axon will be this part. Sort of big snake-looking thing. And then the cell body is this main part. I know that's what that's called, the cell body. It's also called a soma, right? So soma are the cell body. So make sure you know the big parts of the neuron. The cell body is the main part of the neuron, and it controls the flow of the electric body, of the electric signal. So it's actually what initiates an electrical signal. It'll start here, and then it'll go down the axon onto the next neuron. And then the dendrites, they receive input signals. And it sends to the cell body, or the soma. So, you know, these cells, they're all interconnected. So you'll have, if you just think of them as a long line, right, they're not just a long line, they're all interconnected, but I have one here, and it'll send an electrical signal, it'll get picked up by the dendrites, transfer that into the cell body, and then that cell body will send that electrical signal onto the next neuron. The axon will transmit the signal and send to the dendrites. On the next neuron, and then the synapses. These are the connections between the neurons. So our synapses are going to be up here. They're also called the axon terminals. Our synapses. Okay. I like to watch you ever watch the 2-Minute Neuroscience channel on YouTube? It's pretty good, actually, if you're trying to learn about, you know, the neurons and the nervous system and how it works. They just have these little short descriptions of the different parts of the nervous system. So let's watch that. We'll watch those others soon, but we'll also we'll learn about the action and the membrane potentials too, and how we use that in order, our nervous system uses that to transfer information. So there are generally 3 different types of neurons: sensory, motor, and interneurons. The sensory conduct input signals to the central nervous system. And so this would be related to what? We have 5 of them. We use them to smell, see, right, our 5 senses. So this has to do with our 5 senses. And that information from our senses, they conduct those signals to the central nervous system. Remember, you have those, you know, the sensory, it all goes to your integration, and then it sends out a response to that. Our motor neurons will conduct the central nervous system signals to the effector organs. So after the brain has integrated all this sensory input and it determines a response, it'll send that signal to the effector organs. So for example, muscles, if you touch something hot, it'll process that and send it, and you remove your hand or whatever from what you're touching. But also glands too, and other body systems. It's not just voluntary things, but it's involuntary things too. So like if you're sick, it'll send a signal to your brain, it'll integrate that, and then it'll send it back to those, raise your body temperature, change sort of the chemistry of your body to help combat whatever's ailing you. And then interneurons is sort of in between sensory and motor neurons. We're not going to talk about those. We'll mainly be concerned with these two. All right? But you do need to know them at least in name, that you have these three different types of neurons: sensory, motor, and interneurons. Okay? All not new stuff for most of you, right? And that's how you've not been in AMC. But you know, a lot of this. All right. This gets kind of dense, but it's kind of cool, and it brings together a lot of different ideas that we've seen with voltages and capacitances and current and electric fields on how the properties of the neuron allow for the transfer of this electrical signal. So electricity doesn't move in a neuron, as I said, in the same way as, say, in a wire. Like if we have a wire, you know, we think of these electrons moving along through that wire, just sort of in a train almost. It's not exactly how it works in a wire. It's really the energy that moves through the wire through these conduction electrons. But that's how we think of it, sort of like water flowing in a pipe. And that's not really the way that it works in a neuron, but it has the same effect, that I move these charges, or I move this information, like this wave of information, down each neuron until it gets to where it's going. So ions in your neuron, instead of moving, you know, like this across the neuron, they'll move actually perpendicular to the path of the neuron. So ions will move across the cell membrane perpendicular to the axon. All right, so remember, there's the cell body. I can't draw a picture as good as that other guy. And then there's the cell axon, and then the dendrites. So you'll have these ions, these positive and negative ions, that will move across the cell membrane back and forth perpendicular to the axon. And then the motion of these causes the potential in the axon of these ions, causes the potential to change in the axon. And that's what's called the action potential or the membrane potential. Have y'all heard that before? Action potential, membrane potential? Yeah, some of you know. Anyway, it changes the potential in the axon, and then this causes ions to move further down. So it's kind of like a wave, that you have this wave that moves through the axon. And the electrical signal moves down the axon like a wave or pulse on a string. Like with the ropes, right? You do the ropes, and you send these big pulses down. It's sort of like that, where you have this pulse of energy, or this pulse of electricity that moves down the axon. Let's define membrane potential. So first of all, the axon has potassium cations, and it has anions. So that's potassium cations, that's the K. Remember, cations are positive charges, and anions. And anions are negative. And so this is just, it's a general term. It's not a particular element. I mean, there is no element that's A up there. It's just a generic term for any sort of anion. And there are different types of molecules that are negatively charged. These are separated by the cell membrane. From the sodium and chlorine ions in the outside of the axon. And I've printed a figure in your book. So here's your potassium ions and your potassium cations and your anions. And over here you have the sodium cations and the chlorine anions. So they're sort of in between the cell membrane. This is inside the axon, and then this is outside the axon. All right, so these are all moving in a direction that's perpendicular. They're going to move back and forth across the cell membrane, but it's in a direction that's perpendicular to actually the length of the axon. So there's several things going on, and I'm not going to ask you to reproduce all the things that are going on. I'll sort of be clear with you as we move along what I'll ask you to know. But in short, you have more potassium ions on the inside than you do have on the outside. And so by diffusion, because things will tend to move from high to low concentration, by diffusion, you're going to have some of those potassium ions are just going to diffuse across the cell membrane. Not because of electrical forces, not because of any mechanism that's moving them through, but just because there's more over here than there are over here, they're going to diffuse across that cell membrane. They'll just sort of move because at a high concentration and a low concentration, they'll sort of just spread out into that area. Sorry, where was I? So by diffusion, the sodium ions will move inside the axon. Right, these sodium ions are going to move in this direction, and the potassium ions are going to move outside. So the potassium ions are going to move in this direction, only because there's a gradient. There's a gradient of concentrations for the sodium, the potassium, and the chlorine. You're going to get this sort of motion of these ions from one side to the other. So this is the concentration gradient. That's one of the things that causes these ions to move from one side to another. Because of differing permeability in the cell membrane, for sodium, or for potassium and sodium ions, they're more permeable for some than others. You get more potassium ions move out than sodium ions move in. It's just easier for the potassium to move out than for the sodiums to move in. So you get more potassiums coming in and fewer sodiums coming out. Or excuse me, the other way, more potassiums coming out and fewer sodiums coming in. So the inside of the axon will become what? Positively or negatively charged? Negative, right. So the inside of the axon will become more negatively charged. And it's going to have a lower potential than the outside. All right, so I get more of these. More potassiums are going to move out, and fewer of these are going to move in. So I'm losing a lot of positive charges, but I'm only taking on a small amount of positive charges, and so I'm going to have a net negative charge on the inside of the membrane. And negative charge, if you remember when we were looking at our plates, positive, positive, negative, negative over here, this is the high potential side, and this is the low potential side. So on the inside of the cell membrane, I get a lower potential than I have on the outside. That's just because of the concentration gradient, and then also because the cell membrane is not permeable in the same way for the sodium and the potassium ions. That one will move across more than the other. So that means that there is a potential difference between the inside and the outside. Okay? You with me? Let's finish up this section, okay? We don't have long. Hang on. I know this is a little dense. Did I make a mistake? Okay, so in summary, the sodium and potassium ions, they move by 3 mechanisms. There is a chemical gradient. And what that's going to do is it's going to move potassiums out and sodiums in. There's an electrical gradient. And that's going to move potassiums in and sodiums out. And then also, there's the sodium-potassium pump.
So number 2 is supposed to be opposite.
Yeah. And the sodium-potassium pump moves potassium in and sodium out. Yeah, I think that's right. Not sure why these are different. I'll have to look into it. I'm pretty sure this is what I have in my notes. Nervous system, I'm not quite up. Y'all probably know as much as I do about the nervous system. So, but I think that's right. It doesn't seem like it should be right, because it seems like the electrical gradient should take them in the same direction. Okay? Just leave it like that for now. We'll come back to it next time. And then the net result of these means that the inside of the cell is slightly negative. So that gives it a resting potential of about minus 70 millivolts. And this is a technical term, so we'll look at that resting potential a little bit later. Let's watch this video, and then we'll wrap up there. But it reiterates